Now see here, next is Bernoullis theorem. This is applicable for an ideal liquid, that means completely incompressible and non-viscous liquid. It states that for a streamlined flow of an ideal liquid, that means incompressible and non-viscous, the total energy per unit mass remains constant. It means total energy means the sum of the potential energy per unit mass, kinetic energy per unit mass and pressure energy per unit mass remains constant. Now see here, how do we prove this Bernoullis theorem here? So for that, suppose you have taken, this is a ground level here and there is a tube like this, and in this case these are the two area of cross section A1 and A2. This is here height H1 and this is height H2. Liquid is flowing is here in a streamline flow. So flow of liquid is a streamline. Here velocity is V2 and here velocity is V1. Pressure is P1 and pressure is P2. Obviously, P1 is greater than P2. So because of high pressure here, the greater pressure, work is done on the liquid. So work done per second on the liquid is here due to pressure. Liquid rises up and moves this side. When it leaves the tube, what happens here? The work is done by the liquid against the pressure. So according to work energy principle, whatever is the work done due to the pressure or against the pressure, so the change in pressure energy per second is equal to gain in kinetic energy and potential energy. So we can write down here P1 V1 minus P2 V2, that is according to work energy principle I am writing here half mv2 square minus half m, here this is a velocity mv1 square plus mgh2 minus mgh1. Now we can write here according to work energy principle I have written here. So we can write P1 V1 plus half m V1 square plus mgh1 is equal to P2 V2 plus half m V2 square plus mgh2. So now we can write here actually total energy, this is here, this is the sum of the pressure energy, kinetic energy and potential energy at this point is equal to the sum of all these type of energy at the another end. Now you have to get the total energy per unit mass. So we can write divide by mass both the sides. When you divide by mass, so here it will become here, so volume upon mass, that is 1 upon density. So you will be getting P1 upon rho plus mass upon here, that becomes half V1 square plus GH1 is equal to P2 upon rho plus half V2 square plus G, that is GH2. That can be written P upon rho plus half V square plus GH is equal to constant. So this is the statement of Bernoullis theorem. So total pressure energy, kinetic energy and potential energy per unit mass remains constant. So now in Bernoullis theorem we have written here P upon rho plus half V square plus GH is equal to constant. Suppose you divide by G, so you will be getting P upon rho G plus V square upon 2G plus H is equal to also constant, because upon G that means constant. Here this is known as pressure head, this is called pressure head, this is called velocity head, and this is called gravitational head. all these pressure head, this and this have the dimensions of h. So, this is also the part of here the Bernoullis theorem, and also we can show that the total energy per unit volume remains constant. Now, see applications of Bernoullis theorem. First one is here lift on aeroplane wing. You know, according to Bernoullis theorem, total energy per unit mass, that is P upon rho plus half v square plus gh is equal to constant. This is the total energy per unit mass that remains constant at any point. Now, if the horizontal level is same, so the change in gravitational potential energy is neglected. So, we will be getting P upon rho plus half v square is constant. Now, see in case of aeroplane wing, this is the aeroplane wing. Its curvature, it has got the curved surfaces, upper and lower surfaces. Now, the wing is moving suppose this side. So, curved shape is like that, so that the velocity of air above it is very high and below this is the velocity is lesser. So, when the velocity is very high here, so obviously there is a kinetic energy is much higher and as compared to the this below part. So, when the kinetic energy is higher and so the pressure energy will be lesser, and at the bottom what happen here, below its kinetic energy is lower. So, pressure energy is here greater because the sum remains constant. So, here is the pressure suppose P1 and this side is pressure is P2. So, now P2 is greater than P1 due to difference in the velocities upper and lower surfaces. As a because of this, upward lift is acting here, that is P2 minus P1 into area of the wing. This is called upward lift. Because of this aeroplanes goes up or the rises up. Now, see second application here, that is called curved motion of a spinning ball, that is a Magnus effect, that is very important concept here. Suppose see here this is a cricket ball which is spinning like this or rotating about its axis. Because of the rotation of this ball, air around it also is set into rotation and that is rotating in this way. Now, if the ball is moving in the linear motion, that is the linear path, then also the air's streamlines are moving like this, that is dragged backside. Now, if the ball has both the motion, it means spinning as well as linear motion like this, what happens? So, this is the velocity of this streamline drag to the back side. Because of spinning, air has velocity to this side. So, these two velocities are in opposite direction. So, that reduces the velocity, and here the velocity due to rotation and due to this drag both are in the same direction. So, velocity increases. So, when the velocity increases here, so the pressure energy reduces because increase in kinetic energy reduces the pressure energy, and here pressure energy increases. Because of that, there is its path which is actually straight, that becomes curved path. So, this dynamic force due to spinning of the ball is known as actually Magnus effect.